In our first question, we're doing another hardware design exercise where we're designing a microcontroller circuit. So we start off with our microcontroller in the middle, our MSP430. We didn't specifically ask for it, but obviously we'll need a power supply with our decoupling capacitor. Then we need some switches on P1.0 through the P1.3 and some LEDs on P1.4 through the P1.7. So we might draw our LEDs on this side, each with its own current limiting resistor. Okay, so there's all our LEDs, and we can label them P1.4, P1.5, P1.6, P1.7. And then we have all our switches. Now, I've specifically said these need external pull-up resistors. So we have our external pull-up, we have our switch, or in this case our draw buttons, which is what we're more generally using. So there's one, and our last one there. And these are on P1.0, P1.1, P1.2 and P1.3. Okay, in the previous question we need to talk about how we chose our pull-up resistors. In the previous question I didn't actually ask you to calculate or calculate the current limiting or the pull-up resistors, but we've looked at plenty of examples of calculating the current limiting resistors. Let's look at how we calculate the pull-up resistors though. So first thing is we want to make sure they don't float. So we want to ensure inputs don't float. That's really their primary purpose. So we need a few requirements. They need to be small enough to stop the input from floating, so to actually pull the pin up. But they need to be large enough so that they don't waste excessive amounts of current when the switch is pressed. So, quick little back of the envelope calculation. When we're looking at current, we know it's V on R. If we have our current limiting resistor that looks something like this, we have our button there. For the circumstance where we're pressing that button in, so we've shorted that, we're connecting our, in this case, 3.3 volts or 3.6 volts, something in that order, through to ground. We want a current limiting resistor that make sure we have a fairly small current. Up till now we've been using about 10k. Now if we look at that, we've got 3.3 volts divided by 10k gives us 330 microamps. So we're not wasting too much current there. Now we're going to look at some ADC measurements. When we're calculating voltage levels and voltage steps, we remember that if we say to the n, where in this case n is 5, that will give us the number of levels, so 32 voltage levels. And 2 to the 5 minus 1 will give us 31 voltage steps. And think about it this way. These are our discrete voltage levels, there and there and there and there. And these are the steps, so it's always going to be one less than number of levels that we have. What's our step size? Well, we say K is equal to 5 volts divided by 31, which equals 161.3 millivolts per step. How would we encode 4 volts in binary? So we say 4 volts divided by 161.3 millivolts, and this should tell us what step it's in. It's 24.8, which is approximately 25. In decimal, our 25 in binary, we convert that to 11001B. Then we've got this one. Now I neglected to put a B there. It is a binary number. What voltage would 0101 be? So 0101 is equal to 9 in decimal. Oh, sorry, 10. We say 9 times 161.3 millivolts is equal to 1.45 volts. Okay, here we're going to have a flow diagram to implement a 10-bit software DAC, and then we'll write code based on that. So a few different ways we could do it. Essentially we want to specify a period. So we've got 10 bits. Let's say our period, so we'll say start up here. Our period is 2 to the 10. We've got period equals 10 to 3. Then we need to work out what our on time is going to be. Well, we specify that. So in this case, we'll just call it our on time, we'll call it on, will be equal to, well, whatever we make it. 21, 52, whatever it happens to be. Okay, once we've defined our on time, there's two different ways we can go. Firstly, we can set the signal high, delay for the on time, set the signal low, and then delay for the remainder of the period. Or we can explicitly calculate what the off time is going to be, and then delay for the on time and delay for the off time. So we might do the latter of those circumstances, but either one's permissible. So we'll calculate our off time. Off equals P minus on. We'll set our output high. We want to delay for the on time. Set our output low. And we want to delay for the off time. and we loop back around again. Our period being unchanged, but we could potentially change our on time. Now our delay function, pretty straightforward, the sort of things that we've been doing before, so I won't go over that in detail in terms of defining that. Okay, so let's write our code to match up with this. So we'll say int p equals 1023, int on equals, well, whatever we make it. Let's set it to 251, for example. Let's calculate our off, equals p minus on, and well, I guess we can have here a while loop, while one, infinite while loop, and we want to turn it on and off. We're on p1.1, so we want to set that pin high, p1 out or equals bit 1. We want to delay for the on time, so we call that function p1 out and equals not bit 1, so we want to set the pin low, and we delay for our off time, and then we end. Now delay function, we could have something like this, void delay int delay time, and in there we could have a very simple loop for int I equals 0, I is less than delay time, I plus plus, and open close bracket, and that will just delay for however many cycles we specify in delay time. Okay, this question's one where we're setting up the ADC using embedded C. So we're first told we need to write an embedded C function. So let's start by doing that. We say void init, or short for initialize, ADC, no parameters we're passing to it, and we can have all our arguments in there. What we then need to do is work out how we set this thing up. So we're given some registers in the back pages. We need to use pin 1.5 from the ADC. We're using polled mode. We're using VCC and VSS as the references, SM clock as the clock, and no clock divisions. Now we can go through those data sheets and work out a few things. Firstly, our references, VCC and VSS are our references. So these 3 bits at the top of the ADC10 CTL0 register should all be 0. We also note that when the E and C bit, which is down here, is set to 1, we can't actually modify any of these bits. So we first need to set that particular bit to 0. So before we do anything else, we might do that. So we're going to set bit 1 of ADC10 control to 0. ADC10 control 0 register, and we're setting bit 1 to 0. So in the comments, E and C equals 0. That allows us to modify everything else. So we may as well set up the references correctly. So we need VCC and VSS as our references. We also need to turn the ADC on. So we need to set bit 4 to be on. So we set that to 1. And we look at some of the other registers. We're not actually going to be using them. Like, we're not using interrupts. We're using polled mode. So we can set that one to 0. So essentially to set up the rest of this register, ADC 10CTL0, we're going to set the ADC to on, which is bit 4, and the other ones stay as they were because the references need to be 0, 0, 0. Okay, we also have another register that we can use, the ADC10 control register 1. The control register 1 allows us to set the input channel of the ADC. The input channel of the ADC we choose based on what it's connected to. In this case, we've specifically said we're going to be using the ADC on pin 1.5. And if we look at the data sheet for our device, and if we look at what's connected to pin 1.5, it's analog 5 input channel. So pin 1.5, A5, the analog input 5. So in this case we're using A5. So we need to set those top bits to 0, 1, 0, 1. We've also been told that we don't want to use the clock divider. So clock divider should be 0, 0, 0 in that part there. We've also been told that we want to use the SM clock. So bits 4 and 3 should both be set to 1 as well. So let's set up those things now. So we've got our ADC 10CTL1 register, and we're going to set that up as bit 14 or bit 12 or bit 4 or bit 3. So that sets up the correct channel and sets up the clock. Final thing we need to do is we need to enable this enable conversion bit again that we disabled at the start. So we say ADC 10CTL0 or equals, because we're setting it to 1 now, bit 1, and there we go, our ADCs are all set up. A few comments there, E and C equals 1, here we're setting up SM clock, and we're using A5, and here we're turning ADC on.